Chapter 3, Section 4, Rates. We're going to talk about rates of change and visualizing rates. Well, basically what a rate is a fraction. It's another way, a comparison between two numbers. And that's the first definition they give us. And why, kind of the reason why they're given it to us now is because graphs make use of two axes. They allow us to visualize how two quantities change in respect to each other. In other words, what is the relationship between those two numbers? The number occupied by a ratio of 2 units is used to represent this type of change and is referred to as a rate. So what we're going to do in this section is look at a lot of things, or go through some examples mostly, that because this is the only piece of new information in this whole section, is the definition of a rate. And in this yellow box here, it says a rate is a ratio. Ratio means fraction. And when we talk about rational numbers, that's by definition is any number I can write as a fraction using integers. So that's where we get that rational from, rational, right? R-A-T-I-O and then N-A-L for rational. And I guess I don't know how that relates to the English word used for rational now, which usually changes all the time with time. So, but in this case with algebra, when we talk about mathematics and stuff, a rate has a specific definition, and it's the relationship or the fraction created between two numbers or quantities, and then we look at how they change in respect to each other. So, and that's really what a graph, a two-dimensional graph, does. And okay, so let's look at rates that we run into all the time. A website grows by 10,000 visitors over a period of 2 months, has an average growth of a rate of 10,000 over 2, or 5,000 visitors per month. And if you put a 1 in front of that month, you'd say visitors per 1 month, or this fraction simplifies to be 5,000 over 1. And most of the time we express rates with the denominator of the fraction being 1. And I think that's why we kind of forget, or it's easy to forget, that they're really a fraction. Well, vehicles traveling, we do that a lot. We talk about rates. In fact, we have a speedometer in our car that really is giving us a rate of change, really, on how far you will go if you maintain this certain rate. It's telling you something in miles per hour or kilometers per hour. So there's a comparison between the amount of distance traveled and the amount of time. So let's look at a vehicle traveling 150 miles in 3 hours. It is moving at a rate of 150 per means division, 150 miles per 3 hours. Or if I simplify that fraction, it would be 50 miles per 1 hour. I could write that as 50 over 1, which means 50 miles over 1 hour. And like I said, we tend to stick with rates. We create the denominator is equal to 1. Now a class of 25 students pays a total of $93.75 to visit a museum. The rate is then $93.75, that amount of money, per the amount of students, so per 25 students. Well, we may want to find out what the cost per one student is. And really, when we're talking about it, you got to be careful. That could be an average, especially when you're traveling. If we're going to go 150 miles in 3 hours, we say we go at a rate of 50 miles per hour. Well, that is not true, is it? It's not really, we don't start the car and it jumps to 50 miles per hour immediately, and then we stick it right to 50 miles per 1 hour and then travel for 3 hours, right? Even with this kind of, probably not here with students, but depending on the age of the students, there might be some different rates for different students. But the total cost over the total amount of students will give me an average per one student. So you get this $3.75. And then it says caution: to calculate a rate, it's important to keep track of the units being used. That is very important. In fact, it's very powerful, really, is that we can use, by thinking of units like miles and hours and, distance in, meters or feet, and time. That comparison happens a lot. Is it hours? Is it minutes? Is it seconds? Those kinds of things. It really makes a difference. So the caution is to do that, but we're going to go through a couple things with conversions to show how powerful it is to use the labels, or the amount of distance they're talking about, or amount of time, amount of volume, those kinds of things. Well, in this example, car rental, it says on January 3rd, Alicia rented a Chevy Cruze with a full tank of gas and 9312 or 9,312 miles on the odometer, which indicates how much distance that car has traveled. On January 7th, she returned the car with 9,630 miles or 9,630 miles on the odometer. And if the rental agency charged Alicia $108 for the rental and needed 12 gallons of gasoline to fill the gas tank, find the following rates. Well, so they give us some information, and then the question really is going to set up the fraction. If we look at this, it says the car's rate of gasoline miles in miles per gallon. Well, we know that it used 12 gallons, and we also know with some calculation how many miles she traveled. Here's the gas mileage, right? But here's the fraction: miles per gallon. The number of miles traveled over the number of gallons. This gives me the whole thing right here. Translate this into an equation, or into an expression in this case. I would go miles divided by, or miles fraction bar, gallons. B, the average cost of the rental in dollars per day. Dollars, the amount of money she spent over the amount of days she had the car. The car's rate of travel. Miles, again, they got this naming here, but here's my fraction: miles per day. Amount of miles traveled per the amount of days that the car was rented. And that's what they go through. Well, we need to, like I said, we need to calculate. We take the difference between the odometer readings and we'll get the amount of miles, which is 318 miles. They give us 12 gallons, right? So if I want this first one, A, miles, right here's miles over gallons. There it is. Now, again, when we're doing this, they say use division, and probably if this is a place where I think it's okay with fractions to use a calculator, because we're going to really divide 12 by 12 and to get this equal to 1 gallon. We could also think about that. What could I divide this by that doesn't really change any values? And you end up with that magic number 1 in a way. Because really what I want the denominator to change from a number that's not 1 into 1. And how do I do that? I actually do the division by this denominator. So what we end up with is 26.5 miles per 1 gallon. by that division. Still a fraction. This fraction is equal to this fraction. We just express rates with the denominator equal to 1 of something. Okay? Well, B, they were looking for dollars per day. Put the dollars that were spent over the days. Same process. Miles per day. There's my fraction. Miles over days. Simplify in a sense, or get the denominator equal to 1 day in this case. And really that's all there is to rates. And then here's another caution, and these are really good to pay attention to, is that usually they're trying to point out where there's a lot of errors. It says units are a vital part of real world problems we must consider in translation of a problem and include it in the answer to the problem. You know, if you said, if they were asking for miles per hour and I said 50, I would say 50 what? Because, you know, just like that one first example, there are 3 rates that they were asking for, and so on. So make sure you keep your labeling with it, and then translate that into what we're used to saying for rates, that per. So many problems involve rate of travel or speed. Speed is an object is found by dividing the distance traveled by the time required for that travel. And thus the speedometer, right? The speedometer is telling me not exactly how much time it's going to take me to travel. It's really just saying if I stick this speedometer at 60 miles per 1 hour, and if I really kept discipline and kept that thing, or used like cruise control and stuck it right to 60, how far would I go after a mile? I'd go 60 miles. How far would I go after 2 hours? You know, it'd be 2 times that, or 120, and so on. We use that a lot. Well, let's look at example 2. It says transportation. In the Atlantic City Express bus makes regular trips between Paramus and Atlantic City, New Jersey at 6 p.m. The bus is at mileage marker 40 on the Garden State Parkway, and at 8 p.m. it's at marker 170. Find the average speed of the bus. Well, speed is distance over time, right? And that's what they say. Speed is distance traveled divided by the time spent. So we need to find out what's the distance that occurs between these mile markers. Well, you take the difference of that and you find out it's 130 miles. Well, they tell us that it took 2 hours, so I get 130 miles per 2 hours, or over 2 hours, which is 65 miles per hour in a fraction form, or 65 miles over 1 hour, or 65 miles per hour. Right here is how we usually say that. So it's just a fraction again, and we're simplifying it somewhat in a special way. Well, now here's visualizing rates. We're going to look at some things, really visualizing or drawing pictures of rates, where hopefully we can illustrate and be able to draw pictures. In fact, that's mostly why we do graphing at all, is that we're trying to get a picture of the situation, maybe to predict or to just get a true picture or a true indication of what's going on. And when we get into linear graphs or things that are linear, they create lines, and we can probably get a pretty good idea what's going on from that line. It's not the best method to get the exact values out. To solve equations through graphing is not a good idea, because we end up with our scale of our graph for the grid lines and stuff like that may not fall exactly on a cross of the grid to give us a true where we're sure of the numbers. So we'll talk about that some more too. Well, let's look at this example 3. It's about rainforest. It says between 2004 and 2010, the additional yearly amount of Brazilian rainforest was deforested that was deforested decreased by 1,250 miles squared. You know, don't miss that little exponent. And this is one of the reasons that to the 2 power is called squares, because they're talking about square miles. If you could add flat land and all that kind of stuff, you could go 1 mile by 1 mile and make a square. They're talking about that as a square mile. It's a way to measure area is in squares. Okay, so they're talking about area. During 2004, approximately 10,000 miles squared of rainforest were deforested. Draw a graph to represent this information based on information from the National Institute of Space Research, which is kind of interesting. You think about space research talking about force in Brazil, right? Well, we have things in space that are really should be Earth research, right? Because it's really looking at the Earth from space. Well, the solution is to label the axes and note the rate is given in 1,250 miles squared per year, or this rate of 1,250 miles squared, or squared miles over a year. So in other words, when they're talking about it, you need to look at this rate. The comparison is squared miles over years. That's going to indicate how I need to label my axes of my graph. So we'll list, and this is a choice. We list square miles of rainforest deforested on the vertical axis, and that is a choice. They could say, well, maybe years should go up and down, and squared miles should go left to right. Usually time ends up to be our horizontal axis. We're kind of used to seeing timelines. So this is probably the way you'd choose all the time. Next, we select a scale for each axis to allows us to plot the information that's given, right? I don't want to start marking these out one at a time on a grid, because I'd need about, I'd have to start pasting graph paper together to get the numbers on this thing. So we think about scale and how we're going to fit this thing on the graph, and that's what they're talking about here. So here's the steps. Well, first, if I'm going to draw a graph, I need to have axes, and I need to know what these axes mean. So this horizontal axis is time in years, okay? And this additional squared miles of rainforest deforested, right, is the vertical scale. Now the next thing I need to decide is, well, where am I going to start the numbers at, and how much scale am I going to put up and down, and those kind of things to make things fit. Now with time, I could, we're used to starting at 0 a lot. Do you think I'm going to start at year 0 and go all the way up to 2010? You'd have to have a lot of space over here with no data. So they choose a date range that's going to fit in this data that we're given. Like the first year that they're talking about is in 2004. Maybe not a good idea to start here, so let's just tick over one. And if I look at this, I'm actually going 1 year at a time. So this is really 2003 right here. 2004, 2005, 2006, and so on. Well, and then I need this scale to fit. So at 2004, we're talking at 10,000. I need that 10,000 to be in this vertical range, okay? And notice that these grid lines go up 2,000 at a time. That's a choice to show, how I'm going to decide that. Well, now, when I do this correctly, I have the ability to plot the ordered pairs. Remember, the first number is always a horizontal change from 0, or from your 0 in a sense. In this case would be the grid line that we labeled, right? And the second number is vertical change. So here is an image here that we can draw and look at this data and see that a picture of what they're talking about. I can pull all that data that they talked about in there. In fact, even the first time I read this problem, I was thinking about, usually it's always bad news about the environment. This is really good news. I mean, the amount of forest land that's being deforested is going down, which is good. I hope it isn't because they're just running out of forest, but um, that's pretty good news. At least it's going in the right direction if you're not in the lumber industry, I guess, right? You're into the breathing industry. It'd be a good thing to have some things that are producing oxygen. Okay? So this graph, and the main point of this graph really tells a lot of information very quickly, a lot better than that whole paragraph trying to explain that data. Because I can put that data down here and I can get a good picture of what they want us to see. Okay? So example 4 has something to do with banking. This is Nadia prepared the graph from the data collected in a recent day at the local bank. The rate can be determined from the graph, and we'll look at that. And what is that rate? Okay, remember rate is a comparison of two numbers, right? Well, here we have time, right? But this is time of day. It isn't time, in years or, months or something like that. What are they illustrating here is really a time of day, right? There is a change in time. We could think there's a certain amount of minutes occur between 9 a.m. and 10 a.m. or hours, if I want to do it that way. In fact, that would be the grid lines. If I go from here to here, well, excuse me, it's not, is it? It's actually, these grids are 30 minutes at a time. So from here to here it goes to 9:30, then to 10, 10:30, 11, 11:30, but they just label every other one, right? In the vertical is the number of transactions that occur. So the bank, what she has is she was watching, she would mark down time of day and count how many people were in the bank, probably would be what she was doing. So what's the first question? What rate can be determined from the graph? And they say because the vertical axis, this up and down, shows the number of transactions, and the horizontal axis represents the number of time in 1 hour increments, kinda, right? I said it really is, the grid line is 30s minutes. We find a rate of number of transactions per hour. Okay? And then I can look at these ordered pairs, and it isn't that the rate is what is this, 50, 75, 100, would be 75 transactions happened at 9 a.m. Okay? That's an ordered pair on there. Okay? At 11 a.m., there were 225 transactions, and that's the other ordered pair there. Well, if I want a rate, it's a rate of change that occurs. I'm really talking about from here to this time, which is 2 hours, how many transactions occurred right here. Well, I already had 75 done by 9 a.m. So I take the 75 off and I get 150. So I get 150 transactions occurred in this 2 hour window of time, or I get 150 over 2 hours. There's your fraction. Now you really got to read this and think about what are rates. A rate is a comparison between two numbers, but we're talking about what's happening in a segment of time. And we may need to calculate what amount of things happened in that segment of time. So that's really it. I mean, like I said, there's only one piece of new information. How we apply that can really vary a lot of ways, just like a lot of algebra. But that's it. And now we're setting up really one of the most important rates for graphing linear equations, which is slope. And slope is a fraction which says rise over run. the amount of change from one point to the next point. Well, let's make a fraction out of that, or a rate. We can say, if I go from one point to the next point, how much up and down did I do? That's the rise. And then I put that over, the rise is the numerator, and over the denominator, which is run, which is how much change do I have to move left or right. And that is a rate called slope. And I'll talk about that a little bit more, or obviously more next section, but we're going someplace with this. But we run into these kinds of rate problems in a lot of situations, real world situations, so it's good to go through.